Welcome to Conceptual Physics at Delaware Tech, Chapter 8, Rotational Motion. So in this unit, we're going to talk about what rotational motion is. We'll talk about the concept of rotational inertia, and this is parallel to the inertia that you've already learned about, but now for rotational motion. We'll talk about torque. Torque is kind of the rotational analog of force. It's force that drives things to rotate. We'll talk about center of mass and center of gravity. We'll talk about something called centripetal force, and you might be thinking of centrifugal force, but centripetal force is a real force that draws objects towards the center as they're going around in a circle, whereas centrifugal force is an apparent force. It's actually not a real force. It's just apparently observed by somebody that's rotating. We'll talk about rotating frames of reference, and that is if you are the viewer within something that is rotating. We'll also talk about simulated gravity, the idea of using rotational reference frames and centrifugal-like force to simulate gravity in things like a space station that's rotating. And we'll talk briefly about the concept of angular momentum, and this is parallel to the linear momentum you already learned about, and conservation of angular momentum, which is parallel to the conservation of linear momentum that you've already learned about. So, circular motion. When an object turns about an internal axis, so it's going around an axis, that's the center point, and it's undergoing circular motion or rotation. This is circular motion, and it has a lot of names, but let's talk about the two kinds of speeds that are associated with circular motion. One is called the tangential speed, but it has two other names: linear speed and translational speed. They all mean exactly the same thing. We use them in different contexts. If you hear any one of these, they all mean speed, the speed that you're already used to measuring as things are moving linearly in a line. So that would be represented by this red dotted line here. And if an object is going in a circle, in this case counterclockwise, the way this circle is drawn, you can see that this is like a string with a ball on the end of it that's being spun around in a circle. And the blue curve represents its motion around that circle. The red dotted arrow represents the tangential speed. In other words, at any one moment in time, as it's going around the circle, its speed is always in a direction that is tangent to the circle. It's pointing to the side of the circle. And as the object moves around, the tangential direction will constantly change. And that's because velocity, remember velocity has speed and direction, so the velocity at any one moment in the circle will be changing every moment of the circle. Speed might not. Speed might be constant going around the circle, but the velocity is always pointing in a direction tangent to the circle. Then we have rotational velocity, also known as angular velocity or angular speed, or circular speed or circular velocity. These all three mean the same thing. If you hear me use any one of them, they all mean the same thing. So we have two categories of velocity or speed. The speed going linearly, in other words, how much distance is covered as it's going around the circle. So a tangential speed or a linear speed would be, say, meters per second. It's how many meters around the circle it is per second, or how many kilometers per hour, or how many miles per hour, whatever your units of speed are. It's the distance covered around the circle. So it's going to depend on how big the circle is. Whereas rotational speed or rotational velocity is how many circles you make per time. So maybe one revolution per second, or one rotation per minute, or certain number of degrees per minute, like 90 degrees in 10 seconds. That would be a rotational velocity. Physicists tend to use it in a measure of angle, but not degrees. They use a unit called radians. We know that there are 360 degrees in a circle, but there are 2 pi radians around a circle. We won't be using radians in this class. I just want you to be familiar with it. So they'll often do it in radians per second. If you ever take a more advanced course, you'll see that. We'll be looking at more general terms like revolutions per second or revolutions per minute, RPMs, that sort of thing. So this would represent a rotational speed around the big circle. And you'll notice the the big blue arc and the little blue arc are covering the same amount of circle as the object's rotating. So while the rotational velocity is completely independent of where you are in the circle, except in the center. Center doesn't really count because it's not moving at all. But any object moving around with the rotational speed, it'll be the same whether you're out far or in close to the center of the circle. And this is because you're covering exactly the same fraction of the circle over time. It's a smaller circle for the smaller arc, but it's the same fraction of the circle. Right here it's showing about maybe a third of the circle for both of those two arcs. So they move. Rotational speed is not dependent on the radius that you are out from the center, whereas tangential speed is very dependent on the radius. If you come in closer, you're tracking a smaller circle, and therefore you don't have to move as fast in terms of distance per second. We're not talking about circles per second or rotations, we're talking about distance per second. And if your circle is smaller, the tangential speed will be smaller the closer you get to the center. And by the time you get to the center, there is no velocity in terms of tangential or rotational. All right, so the distance traveled by a point on a rotating object divided by the time, that is the tangential speed. In other words, meters per second, kilometers per hour, all right? And this will depend on where you are. So points closer to the circumference, in other words, all the way out with a big radius, they'll have a higher tangential speed. They have to cover more distance in the same amount of time than the smaller circle. So in this case, we see an ant that's halfway in the circle and one that's all the way to the edge of the circle, and that's going to be moving twice as fast. If you look on the left, you'll see the green arcs. The green arcs show you both the relationship of the tangential and the rotational speed. Both of the green arcs carve out the same slice of pie, the same fraction of a circle in the same amount of time. But the green arc, the smaller green arc, represents the motion, the linear motion of a smaller circle than the bigger green arc. So the big green arc represents a higher tangential speed than the small one, but they both have the same rotational speed. So as I mentioned before, rotational speed, it's the number of rotations or revolutions per time. The star is there to remind me to tell you that not everybody uses that unit. They use radians per time or degrees per time. They're looking at how much of an angle is being tracked. But these are legitimate measures for rotational speed as well. Revolutions per second, rotations per second, revolutions per minute, also known as RPMs, which you might have heard of if you've played any old record albums. They use 33 1/3 RPMs, or the old ones from the 1950s and 60s were 45 RPMs. They were spinning 45 times per minute. So the symbol for rotational speed, remember, tangential speed or linear speed is just a simple V for velocity. But for rotational speed, we use the Greek letter omega. Omega looks like a curvy W. It is not a W. It is the omega. It's the lowercase letter of the last letter of the Greek alphabet. So just to point out how rotational speed is the same no matter where you are in the circle, think about a merry-go-round. If you're on a horse that's on the outside of the merry-go-round and your friend is on a horse that's closer to the inside of the merry-go-round, both of you are finishing a circle in exactly the same period of time. You're going the same number of revolutions per minute, the same number of circles per second, or whatever unit you want to use, identical rotational speed, circular speed, angular speed. But if you're on the horse on the outside, you're covering more distance in the same amount of time. You have a faster tangential speed, and it's going to be proportional to how far you are out from the edge. From the center, excuse me. So here's the formula. Tangential velocity is proportional to both the radial distance, that's just how far you are from the center, or your particular radius, the object's radius, not the radius of the whole circle. It's how far the spinning object is from the circle, times the rotational velocity, how many loops per second, how many loops per minute. So tangential velocity is both proportional to radial distance. They're proportional to each other. Increase one, you'll increase the other by exactly the same fold. Decrease one, you decrease the other by the same fold. And that's also true of tangential velocity with rotational velocity. Triple one, you will triple the other. Cut one in half, you will cut the other in half. And that's represented by this formula. V is proportional to R times omega. Omega is your rotational speed or rotational velocity. All right, so a ladybug. This is the picture we already saw. You should already know the answer at this point. The ladybug sits halfway between the rotational axis, that's the center of the spin, and the outer edge of the turntable. In other words, the whole circle of the record. When the turntable has a rotational speed of 20 revolutions per minute, RPMs, and the bug has a tangential speed of 2 centimeters per second. So rotational is how many circles in a minute, 20 per minute, and tangential speed is how much distance they're covering, 2 meters every second. What will be the tangential speed of her friend who sits on the outer edge of the ring? What about the rotational speed? Well, let's take these one at a time. So I'll let you think about it. We are doubling the radius. What happens to each of these two velocities, these two speeds? Well, we were at a tangential speed of 2 centimeters per second, halfway in, but now we're doubling the radius. So we're going to get 4 centimeters per second. We double the radius, we double the tangential velocity. They are proportional to one another. And rotational speed of both bugs is exactly the same. They both complete a revolution in the same amount of time. They're both going 20 circles per minute, 20 RPMs, 20 revolutions per minute. All right, so an object rotating about an axis, okay, spinning around the center, tends to remain rotating about the same axis at the same rotational speed unless interfered with by some external influence. Okay, what does this mean? It means if you spin something and you don't interfere with it, it'll keep going at the same speed. That's all it means. And this is exactly the rotational version of Newton's first law of motion. This is for rotational inertia. If the object is already moving, it's not going to change how it moves unless you give it a force to change how it moves. So the property of an object to resist changes in its rotational motion is called rotational inertia. We've already been exposed to linear inertia or just plain inertia. This is the resistance to movement. It's the resistance to acceleration by a force. The greater the inertia, which for linear is really just mass, okay, the greater the mass, the greater the inertia, the harder it is to push. You have to add more force to accelerate it. Increase m, or the inertia, you have to increase the force to get a high acceleration, a change in speed, change in velocity. And the same is true with rotational inertia. But a rotational inertia is not simply the mass. It's a slightly more complicated than that. So let's look at rotational inertia. It's going to depend on the mass. I think that's probably obvious. More mass, the more inertia it has. But it also is dependent on how that mass is distributed in the object. Look at this barbell that someone's holding, and they want to spin it around. They want to twist it. Well, it's a lot easier to rotate it if the mass is tight against the center of rotation, which in this case is the hand. It's the axis. The hand is acting as the axis of rotation here, twisting this barbell. But the greater the distance between the object's mass concentration, in other words, how much mass there is near the axis versus how much mass there is outside of the axis, far from the axis, will change its rotational inertia. The more mass you've spread out from the center, the harder it is to turn. It has more rotational inertia. You can prove this to yourself by taking an object like a barbell and try twisting it with the weights real close to your hand and then twisting it with the weights really far. You will find with the same amount of force, you will find it much easier to turn the one where the weights are tight against your hand. I think you can probably picture that. So greater inertia if the weight is spaced way out from the axis. The more weight out there, the bigger the rotational inertia, the harder it is to spin with the same amount of force or energy. And this greater rotational energy makes it harder to rotate, all right? And tightrope walkers take advantage of this. If you've ever seen somebody on a high wire with a pole, that pole is there to add extra mass far from the center of their body. They're putting that mass out there to give themselves a large rotational inertia. They are making it hard to turn, specifically to turn off the high wire and fall down. By having this weight spread out, the more weight they have sticking out, that's why the long poles work better, the more weight that sticks out, the easier it will be for them to stabilize so they don't rotate off the high wire and fall. So let's look at a pencil. Pencil can rotate in a lot of different ways. Let's look at 3 pencils. They all have exactly the same mass, the same dimensions. So it's the same M, but what's different is how you're rotating them. In the first case, we're rotating the pencil along the axis that runs the length of the pencil. So picture a pencil just sitting on a table and you push it and it rolls. It's pretty easy to do. It doesn't have much rotational inertia. It's very low rotational inertia, so you don't have to add a lot of force to get it accelerated so it's moving. But now, instead, take a pencil and spin it from the center, and so it's whipping around almost like a propeller. That's considerably harder to do. The mass, most of the mass, is not right tight up against the axis like it is in case 1. In case 1, almost all the mass is next to the axis of rotation, the length of the pencil, right through the lead of the pencil. All right. Whereas now, a great chunk of the mass is far away from the rotational axis. And if we look at the third case, now we're putting the rotational axis on one end of the pencil, and we're spinning the whole pencil around as if we're whipping this pendulum around in a circle, but we're holding one end of it. And this is the hardest still because most of the mass is really far away from the axis of the rotation. The further you spread that same amount of mass, the harder it will be to turn, the higher rotational inertia. And in fact, we have formulas for a wide variety of shapes. You don't have to memorize these. These are all in your formula sheet, so it's right there. But I want to point out that all of these formulas have a certain format to them. They're all inertia, the rotational inertia I, is equal to mass times some length squared. And then there's also, sometimes there's a constant there. So it's some constant, 1 or a half or 2/5 or a third, times m, the mass of the whole thing, times some linear dimension squared. And most of these cases with round objects, that linear dimension is the radius, okay, half the diameter. And if we look at the simple pendulum and the first hoop, the hoop about a normal axis, normal just means perpendicular to the ring, so it's going through the center of the ring, and you're spinning the ring as you would say rolling the ring, okay. In those cases, all the mass is is all the same distance from the center. It's all the distance of the radius from the center. So that formula is very straightforward. It's mass times radius squared. But if we spin the hoop differently about its diameter, in other words, we put a string right through the hoop from one side to the other and spin it around that way, almost like the old style propeller hoops. In that case, some of the mass is really close to the axis, like at the top and the bottom, but some of the mass is pretty far from the axis on the sides. And because of that, its overall average value is 1/2 mass times radius squared. So it's half the inertia of the same loop spun in a different way around its normal axis. If we look at the two figures on the bottom right, the solid cylinder and the solid sphere, you see in the solid cylinder, the mass is also distributed. Some is close, some is in the middle, some is far away from the axis that's running through the cylinder, and therefore it's also 1/2 mr squared. A solid sphere, so it's completely got mass all the way through it, it's on average 2/5 mr squared. And we can make comparisons between these 5 that I just pointed out, not the 2 rods in the bottom left. Okay, the sticks are different because we're not using the radius, we're using the length of the object, and you can't do a direct comparison. It requires a little bit of math that's outside of this course's scope. But you can look at the other 5, and all you have to do is see that they all have mr squared in them. So the only thing different is that coefficient. In the first 2 cases, it's just 1 mr squared for the pendulum and for the hoop with the normal axis. Whereas the hoop with the diameter and the solid sphere, it's 1/2, and the solid sphere I'm sorry, the solid cylinder is 1/2, and the solid sphere is 2/5. So you can compare inertias by just those constants. It tells you which one has higher or which one has lower, as long as they have the same radius dimensions and the same total mass. Total mass. All right, so let's look at a problem here. We have a hoop and a solid disk. They're of identical mass and radius. So the M is the same, the R is the same. They're released from the top of the incline at the same time. Which one reaches the bottom first? The hoop, the disk, they both reach it at the same time. Not enough information. Well, we're talking about rotational inertia, how hard it is to spin. And first I want to point out the hoop. We already know the formula for rotational inertia for that. It's just mr squared. It's if all the mass is at a radius of r away from the center, the formula is mr squared. The disk, however, we don't have a disk in that formula, but we do have a solid cylinder, and a disk is just a slice of solid cylinder. It doesn't really matter if that cylinder is long or short. The length of the cylinder is not in the formula. It's just the radius and the mass. That's it. So a disk is just a slice of a cylinder. It's just a really short cylinder, and the formula for that is 1/2 mr squared. So you can see that if they have the same m and they have the same r, the cylinder, in this case the disk, has exactly half the the rotational inertia of the hoop. So the disk will reach the bottom first because it has less rotational inertia. If we compare the two formulas, it has half the rotational inertia of the hoop. Hoop, all the mass is spread out, harder to spin it. The disk, it sums in the middle, sums far out. It's spread out. And as a result, because the hoop has a larger inertia, it's harder to gain speed. It takes more force to get it up to the same velocity as the disk is. So the disk will win the race. All right, so let's talk about torque. Now, torque is the force, it's the rotational analog of force. It's not exactly the same thing as force, and in fact, it's calculated using force and other things, but it is the rotational equivalent of force. And so this is the tendency of a force to cause rotation. So it's not exactly force, but it's close. So it's a case where a force is being used on some lever arm to rotate some object. And in this case, the center of rotation in this picture is the nut that the wrench is turning, the nut or the screw that it's turning, the bolt, whatever you want to call it. The wrench is turning it, and you're applying a force. In this case, the force is applied exactly perpendicular to the wrench. So we have a lever arm, and we have the force, and we have the rotation that results from this torque that combines the lever arm and the force. So this is dependent on the magnitude of the force. That's probably obvious to you at this point. But it's also dependent on where that force is applied. And in this case, it's the length r away from the center. And it's also dependent on what angle it is when you pull that force. So we have what's called a lever arm. Now, a lever arm does not have to be, a lever arm is a theoretical line. It does not have to be the same line as where the wrench handle actually is. And we'll talk about that in a minute. But you have this force pulling on it. So you increase the force, you're going to increase the torque. You're going to increase the distance away from the rotational point, the center. In other words, you make a longer wrench, you're going to have more torque. Torque wrenches tend to be really long. You can use the same force and get a lot more torque out of them by just extending the length of the wrench. And the angle between them, 90 degrees between them is the best angle, because all of your force gets used to drive this entire lever to turn whatever you want to turn. So the torque is equal to the lever arm length, not the wrench length, we'll talk about that in a second, times the force. In this case, because they're perpendicular, the lever arm length is the wrench length. It's the same number, all right? But it doesn't have to be. So torque is we use the Greek letter tau, the lowercase tau. It's just a curvy t, okay, for torque. And it's just equal to the lever arm length. And we'll talk about what a lever arm really is. It's not the length of the wrench. It's something theoretical, times the force that we apply. So the lever arm will depend on two things: where the force is applied, in other words, how far out, that R value, and which direction it acts. Is it perpendicular, or is it some angle, or is it steep, or is it completely pointing out? In which case it won't do anything. No matter how hard you pull straight out from the lever arm, you're not going to rotate that nut. So let's look at a couple examples. We've already looked at one of these, which is very similar to the other. The lever arm is a theoretical vector. We haven't drawn it yet. That's different. All the examples we've done were with the lever arm being right along with the length of the wrench, right? But it is the shortest line from the axis of rotation, which in this case is the nut that's being turned, to the direction of the force, which in this case is the arm. Okay. So in the first picture, we have the lever arm is exactly the same as the length of that wrench handle. And in the second case, it's also equal to the length of the wrench handle, but the wrench handle is just longer. And that is because they're perpendicular. The lever arm is always perpendicular to the direction of the force, no matter what angle you actually pull on or push on. So what do I mean? The lever arm is not always the actual lever. It's not always the actual wrench in this case. So here's an example where you're pulling not at a 90-degree angle anymore. But the lever arm is always a line that is perpendicular to the force. And this is taught in two different ways in different physics textbooks. This is one of the way. I actually like a different way that I'm not going to cover here, but if you're interested, you can come to me and I'll be happy to explain it to you. The math ends up working out to be exactly the same, but how to conceive of it is slightly different. So in this case, this third case here, the lever arm is not along the length of the handle, but the lever arm, that theoretical line, is still perpendicular to the line of force. So you figure this out, you determine where that is by drawing your force line and just extending your force line. So I'll extend the force line from your hand. Obviously there's no hand down there, but you just follow that line down. And then you find the shortest line between the axis of rotation, which is just the nut that's turning, and that between that and the force line. Well, that line, the shortest line, is always going to be the one perpendicular to the force, and that's shown here in blue dotted line and showing you the right angle. So that's the lever arm. In this case, it's not the same as the handle of the wrench. You will not be responsible for calculating these things. You would be given a lever arm length, whether it's on the lever arm or not, and you'd be given a force and you'd be expected to get torque, or one of those three values if I gave you the other two values. We're not going to confuse you with the angles that are used and the formula, because that involves some trigonometry. All right, so here's a fairly simple problem that looks complex. Suppose a 250 Newton girl is in her swing. So she's hanging down, you can see her hanging down in the swing there, is suddenly handed a 50 Newton bag of apples. How far should her swings be set from the pivot? The pivot is the fulcrum, the thing in the middle of the seesaw, in order to continue to balance the 500 Newton boy who is 1.5 meters from the pivot. All right, well, think about this. Torque has to be balanced. He's pushing down and she's pushing down, but what does that really mean? He's pushing clockwise. He's making this thing rotate clockwise, and she's making this thing rotate counterclockwise. They have opposite torque directions. And in order to keep this thing from teetering back and forth and her falling all the way down or him hitting the ground, they have to be balanced. The torques have to be identical. And what that means is her weight, her force, times her distance has to be equal to his weight times his distance. The two torques have to be the same. Obviously, they would have different directions. If we put signs, one would be positive, one negative, but we don't need to do that. We're just looking at how big the torques are. And his torque, so I'll let you think about this. I'll give you a second here to ponder. Well, let's look at this. The answer is 2.5 meters from the pivot. But let's explain where that number comes from. First of all, we know that torque is equal to force times the lever arm length, that theoretical length, but in this case, it's a real length. All right, and his torque, he's 500 newtons, that's his force, down, and it's perpendicular to the seesaw, so it's right down, times his distance from the rotation, that's the fulcrum, the pivot. He's 1.5 meters away, so 1.5 meters times 500 newtons is 750 newton meters of torque. You might remember that Newton meters is a joule of energy, but this is not an energy thing, so we never use the term joules for these. We call it Newton meters for torque. That's the unit. But this means that she has to have exactly the same torque, 750 Newton meters, just pointing in the opposite direction. Now look at her right now. She's 3.3 meters away, and then she's hanging down 4 meters. And if you do a 3, 4, 5 right triangle, you realize that makes her 5 meters away from the point of the fulcrum. But we don't care about that. She is hanging perpendicular to the seesaw. That means her force times her distance from the point of her force, which is 3 meters away, not 5 meters away. She's exerting the force on the seesaw, not from her seat. She's pulling at the seesaw. So it doesn't matter how long her seat is hanging. She could be hanging 100 meters down. She's still pulling on that seesaw 3 meters from its fulcrum, from its pivot point. So that's the number we're looking at. And 3 times her 250 newtons is another 750. They match. But here's the problem. She was given a bag of apples that has a weight of 50 newtons. She doesn't weigh 250 newtons anymore. She weighs 300 newtons. So she's now 300 newtons, and 3 meters is too far away. It will give too much torque. 3 meters times 300 newtons is 900 newton meters of torque. She only wants 750. So 750 divided by the 300 that she is will tell you the distance that will work. So we divide Newton meters by just her new newtons, and we get 2.5 meters. In other words, she has to scoot in another half meter so that she's balanced him. She's overbalanced him if she has that bag of apples. If she moves in a little bit, she's perfectly good, because 2.5 meters times 300 newtons, that's 750 Newton meters, is the same as his 500 newtons times 1.5 meters. They always have to be the same product. Force times the length equals the force times the length. And they can be different forces and different lengths as long as they balance. All right, center of mass and center of gravity. These are pretty similar concepts. The center of mass is just the average position of all the mass. You can say you have a giant rock. Well, somewhere in that rock is the center of all the mass that's surrounding that point in the rock. And it all averages to a certain point in space in the middle. And that would be its center of mass. And because gravity is usually the same throughout the rock or whatever object you're interested in, a human body, something bigger, generally the center of mass is exactly the same as the center of gravity. The only time that doesn't work is when you're working with very big objects where the gravity might be different on one part of the object than the other part, like a planet or a moon or something like that. But in general, they're the same. So we usually refer to them as the same point for our purposes. All right. And if you ever want to figure out the center of mass of a weirdly shaped object, just hang it up on one end of the object. When you hang it, it'll spin a little bit on that one nail that you've got through it. And eventually it'll settle so that half its weight or half of its mass is on the left and half of its weight or mass is on the right. Then you take the thing and hang it on a different part, usually on the outside of the edge. And you can do this with a map of the US, as long as it's the same thickness all the way through. And you can hang it from the state of Maine. And when you do that, you'll see half the mass will be on the left and half the mass will be on the right. And you keep making a line that shows you the halfway point. They show a what's called a plumb line. It's just a string with a heavy weight at the bottom of it, and it just hangs down. You make a little line, and you hang it from another place. So every time you're hanging it, half the mass is on the left, half the mass is on the right. You turn it again, half the mass is on the left, half the mass is on the right. And where those lines intersect, that's the point where anytime you're on one side of it or the other, half the mass or half the weight is there. And that would be the center of gravity. So you can actually do this on your own, and you'll eventually find it. If you did this with a map of the contiguous 48 states, the lower 48 of the United States, you'll find this line passes somewhere through Kansas. Kansas is the center, the geographical center of the lower 48 of the United States, our contiguous 48 states, not continental. That would include Alaska. We're not including Alaska here. So that's the center of gravity, and that's how you find it, by just crossing those lines. Now, the center of gravity becomes important when you're building structures, especially big structures where stability is key for saving lives. And here's a picture of the Leaning Tower of Pisa. Now you might ask, why hasn't it fallen down? Well, there have been times where it was about to fall down and they moved it up just a little bit. They propped it up a bit. But the idea here is that the center of gravity, the center of its mass, the center of its weight, as long as that center, if we drop a line straight down, if the line goes right through the base, in other words, the line is not outside of the body of the tower. If the tower was leaning too far and we put the center of mass, the line would go outside of the bottom of the base of the building. And then we know it's not stable. It's going to fall because most of its mass wants to rotate that building down to the ground. But if most of the mass is keeping it in the ground, it won't rotate down into the ground. So one way to test for stability of a standing object is to look for the center of gravity, draw a line straight down. If you're still within the base of that building, you're probably okay for that type of stability. Now, obviously, there are a lot of other engineering issues you'd have to deal with, but this is just one. So if it falls outside of the base, it's definitely unstable. So now let's talk about something very different here. We're going to talk about centripetal force, not centrifugal force, centripetal force. And this is a real force that people don't realize is even there. Centripetal means center seeking, because when you're spinning an object, say you've got a can on a string or a rock on a string or whatever you're spinning, that object is constantly being pulled towards the center. And you might think, well, no, it's not. It's staying the same distance. But what you have to understand is the can is always moving tangential to the circle. It's always moving in a straight line. And as you're spinning it, you are constantly changing its direction. It wants to go this way, you're spinning it, you're changing its direction constantly. And that means you're changing its velocity constantly, because velocity has speed. You're not changing the speed necessarily, but you're definitely changing direction. So that means you're changing the velocity, even though you're not changing the speed. Change in velocity is, by definition, acceleration. And it turns out, if you actually looked at the vectors and you say, okay, this is where it wants to go, tangential, and this is where the new direction it is going as it's going around a circle, you could calculate, oh, the force that's making it change in a circle every moment in time is always pointing to the center. No matter where that can is, the force lines are always pointing from the can to the center of the circle, to the axis of rotation. And this force is called centripetal force. So to whirl a tin can at the end of a string, you pull the string, you whip it around, you exert a centripetal force that keeps the can moving in a circle. That force pulling inward is constantly changing the direction of the can as it's going around a circle every instant in time. That's an acceleration because you're changing velocity's direction. So centripetal acceleration depends on two things, and two things only. The tangential velocity, that's just how many meters per second it's going around in the circle, and how big the circle is, the radius of the circle. That's it. Only two things. And I'll show you the formula for that in a second. Centripetal force, remember, force, we learned from Newton's second law, is just equal to mass times acceleration. Well, if we have the formula for acceleration, we just multiply it by mass, and we get the formula for centripetal force. So here are the formulas. Centripetal acceleration is the tangential velocity, that's the v squared divided by the radius. What that means is the centripetal acceleration is directly proportional to the tangential, the linear velocity around that circle, squared, and it's also inversely proportional to the radius. In other words, how far away from the center it is. That means if you increase the tangential velocity, you will increase the centripetal acceleration by square of that value. If I triple the velocity, the tangential velocity, or the rotational, but we're not getting into that. If I triple the velocity, I'm going to triple the acceleration. I'm going to threefold squared, ninefold the acceleration. So tripling the velocity will have a squared effect on the acceleration. If we look at the radius, it is inversely proportional to the acceleration, centripetal acceleration. They are inversely proportional to one another. Anything I do to one will happen in the opposite direction to the other. If I triple the radius, I will cut the acceleration in thirds. If I cut the acceleration, if I make the radius 10 times bigger, I will make the acceleration 10 times smaller. So they have the opposite effect. Whatever fold happens to one, it's the other fold happens in the opposite direction to the other for radius and acceleration. And for centripetal force, you just multiply mass times it, because mass times an acceleration is the force. So the force that an object is being pulled in is just mass times that value. So centripetal force is proportional to the mass, that's on the top. It's proportional to the velocity squared, that's on the top. And it's inversely proportional to the radius, that's on the bottom. In variable form, it's written like this: A equals v squared over r, and F is equal to mv squared over r. Just put an m in there, multiply m times your acceleration. So let's look at this in action. When a car rounds a curve, the centripetal force prevents it from skidding off the road. Remember, there is a force, there's a net force pulling the car in towards the center. You might not think that because you're being thrown out to the side of the car and you think, oh, no, the force is the other way. No, the reason why you think the force is the other way is the car, your body continues to move tangent to the circle in a straight line. Every moment in time, your body thinks it's moving straight ahead, but the car is turning to the left. Your body, you think you're sliding to the right. What's actually happening is the car is sliding to the left and yours keep going in the same direction. So it feels like you're being thrown to the right, when in fact what's really happening is you're going in the same direction. The car's going to the left and slamming against you. That's what slamming away from you in that case. So the centripetal force is not a force that is created directly. It's usually created by something else. And in the case of a car going around a curve, there are two main factors that keep a car from skidding around. One is the friction of the road between the tires and the car, and that's what provides the centripetal force towards the center. And there's another one, which I'll talk about in the next slide, that involves the normal force of the ground pointing up into the car. All right, so you've got this force, and if we, so it's what prevents you from skidding when you go around a curve. But if the curve is wet, there's going to be less friction. You are more likely to go in the direction that you would have gone tangential to the curve, which is shown in that blue arrow. The centripetal force is what's pulling you towards the center. And as a result, if your force from the friction is not enough to keep you pulled in from the centripetal force, your centripetal force is smaller, and you'll just keep going in the same direction instead of curving, and that's when you have skids and slides off the road. So how do we prevent that? Well, a lot of highways, especially where you're going to be going fast, are banked. In other words, they're tilted at an angle. Now, why is that important? How does that help? Well, remember, the weight of the car is always straight down to the center of the earth. M times G, mass times gravity, is your weight. But the normal force that keeps you from going through the ground, the force that the ground provides to keep the car from going through, that normal force is always perpendicular to the surface of the ground. Well, if you're on flat ground, it's pointing exactly away from the weight. One's pointing up, the normal's up, and the weight is down. But if you're on a banked curve, your weight is still pointing straight down, but your normal force is at an angle. Your normal force is perpendicular to the road, the new road, that's at an angle. Now, why is that important? Well, it's important because forces at an angle, you can break into component forces. And if you use the parallelogram rule, you'll create a rectangle, not just a parallelogram. You'll have a component that's going straight up, and you'll have a component that's going towards the center of the road. And that's always going to be changing as the car is moving around the circle. The one will always be pointing up, and the other will always be pointing towards the center, no matter where you are on this banked curve. What that means is you now have two forces that you can look at separately that came from the normal force. All right, the car is not accelerating in a vertical direction. In other words, it's not flying up in the air and it's not sinking through the ground. So we know that the normal component that's vertical, the n sub y, must be exactly equal to the weight of the car. They balance each other perfectly so the car is not going through the ground or floating up above in the air. They have to be identical. So that component must be identical. And the remaining component of the normal force is pointing to the center. That's the n sub x, the one that's pointing into the center of this curve. That part is the centripetal force. That's what's generating the centripetal force for this car. It's what's keeping it on the road and not flying out like it wants to if it was just to go straight instead of curved around the road. And what we have here is that the N sub x is the centripetal force. It's mv squared over r. And the y component, the vertical component of the normal, is just the opposite of the weight. It keeps you from going through the ground. So one keeps you on the curve and one keeps you from going through the ground. But they add up to a normal force that's just perpendicular to whatever angled road surface that you're driving on. So if you were to do this with vector sums, this is outside of the scope of the course, if you actually added the n, the original n, the composite n, and the velocity, I'm sorry, and the gravity force, mg, down, those two just equal, remember the ny part is canceled out by gravity. So when you add up these two vectors, the solid red and the solid blue, you will only be left with the n sub x. That's all this is saying. Okay, so suppose you double the speed while rounding a curve. By what factor must the centripetal force change to prevent you from skidding? Another way to ask this is, we double the speed, what happens to the centripetal force, assuming we don't fly off the road? Well, we know that centripetal force is proportional to the speed squared. So if we double the speed, we're going to quadruple the centripetal force. Centripetal force is mv squared over r. It is proportional to v squared. Whatever we do to v, we square that, and that's what will happen to the force. That's also what will happen to the acceleration, the centripetal acceleration. So because the tangential speed is squared in the formula, you increase it, the tangential speed twofold, the centripetal force will be twofold, or fourfold. What happens if you're taking a sharper turn and half the radius? In other words, we're cutting r down to half. We're dividing r by 2. Well, remember, what factor will the centripetal force need to change to keep from skidding? In other words, you're taking a tighter turn, centripetal force is definitely going to change. And we know radius is inversely proportional to centripetal force and centripetal acceleration. You increase the radius, you'll decrease the force. You decrease the radius, you increase the force. So if we're cutting the radius by 2, a factor of 2, we're decreasing it by 2, halving it. That means we're going to be doubling the centripetal force and the centripetal acceleration. And that's because they're inversely proportional to one another. You half one, you'll double the other, and it goes either way. Centrifugal force. Now, this is the one you've heard of, but it's not actually a real force. This is an apparent force, an apparent outward force. So if you're inside the rotating object, you feel like you're being thrown away from the center, not pulled toward the center. And that's because the object that you're in is being pulled towards the center. You feel the walls of the object pushing against your back, and you perceive it as you being thrown backwards, when in reality, it's the wall being pulled towards you, so you feel like you're being thrown back. It's a physiological perception. It's not a real thing, and it's only perceived if you're inside the rotating object. So, it's a common misconception that centrifugal force pulls outward. It's just what it feels like. Remember, you're always going in a straight line. That straight line is constantly changing direction. The centripetal force pulls you towards the center in order to change your direction. You're constantly being curved towards the center, but you never quite make it because you're going around in this circle. Your speed may be the same, but your direction is always different as you go around the circle. So that's the centripetal force doing it, and it makes you feel like you're actually being thrown out, when in reality you're trying to go in the straight direction, and you're constantly being changed where that straight direction is. So and you know that because if you take an object and spin it around on the string, and if you were able to cut the string, you could just let go of the string. If you had a rock on a string and you're spinning it around and you let go, that string is not going to go straight out from you. It's not going to continue in a circle. It's going to go whatever direction it was last when you let the thing go. which is tangent to the circle shown in this green dotted line here. That's how you know that the current velocity of the object going around a circle at any one moment in time is actually a straight line that's perpendicular to the radius and tangent to the circle that it's going around. It's always a straight line path. It's just constantly being changed because of this centripetal force pulling the object in towards the center. If no force was acting on it, it would just go straight out. That's the last force that was put on it, was that direction, or excuse me, the last velocity was in that direction, so that's the way it'll go, and that's Newton's first law. So centrifugal force in a rotating reference frame, in other words, you're inside the rotating object, is a force of its own right. It can feel as real as any force, but it's not really real. It's the force you feel if you're inside the rotating frame of reference. So while it feels as real as any other force, and it is sort of, it's not really a real force if you're outside of the reference frame, outside of the rotation and looking. If you were looking at this little girl spinning the thing, you don't feel that force. You can see the cup is constantly being pulled in a circle, pulled towards her, which creates the circle movement, the circular movement. But if you're a bug inside that cup, your experience is quite different. The bug at the bottom can't tell that the whole world's rotating. It only knows that something's pushing against its back, but it feels like it's pushing against the bottom wall of the can. And that's how you perceive centrifugal force, when in reality it's centripetal force pulling the can into the bug at any moment in time. So centrifugal force can be used to simulate gravity in space stations in the future. We don't have these yet, but people have been talking about these for at least 50 years. If you ever watched the movie 2001 Space Odyssey, I think that movie came out in about 1971, 1974, in that ballpark. They had a rotating space station in there that was beautifully filmed. I highly recommend watching it to see people running around the circle of the space station. So by having a spinning space station, you can simulate gravity for the occupants of that space station on the outer wall, of the inside of the outer wall of the circular space station. It's really the apparent centrifugal force that they're feeling, that they think they're feeling, that will create a gravity-like force so that they're always on the wall of this curved structure. And it turns out, if you do the math on this, it doesn't take a really fast spinning space station to make this work. It turns out if you make the space station big enough, in other words, your R is big enough, you don't need, you can have a radius of 1 kilometer. That means it's 2 kilometers wide, about 1.2 miles in diameter. It's a pretty good sized space station eventually. But if you have this thing spinning, and it's only spinning at a rate of 1 revolution a minute, now that's a lot of distance. Remember, it's a diameter of 2 kilometers, so the circumference is 2 kilometers times pi, so it's over 6 kilometers around. Okay, that's about 3 or 4 miles around. If you spin that thing so it makes 1 full revolution in a minute, somebody in deep space will feel like there's gravity on the ground, on the inside surface of the outer circle. They have to be on the inside surface of the outer circle. And that is enough to simulate about 10 meters per second squared of acceleration. That's the acceleration. That's actually the centripetal force, but you feel it as centrifugal force. And it will work out to about 10 meters per second squared, which is about what gravity is. So this is all you need to be able to do it. It's a lot of technology, but it's not impossible technology. And so let's move on to the next topic here, angular momentum. So angular momentum is like regular momentum, but now for spinning objects. It's analogous to linear, which we called momentum with an abbreviation P. Angular momentum we abbreviate with a capital L. So it's equal to the rotational inertia times the angular velocity. Rotational inertia is our I that we looked at before. It gets bigger if you spread the mass out far from the circle. And our angular velocity is how many loops, how many rotations or revolutions per minute, per second, whatever. And if you multiply those two, you'll get the angular momentum. So this is analogous to linear momentum, which is just mass times velocity. If you look at the two formulas, you have the two momentums are both multiplied by something that relates to mass, rotational inertia, or just regular inertia, which is mass. And then it's multiplied by velocity. In the case of angular, it's multiplied by the angular velocity, omega. And in the linear, it's multiplied by the linear velocity, v. So they're really different versions of the same formula. It's just the rotational version of the P equals mv. L equals I omega. All right. Now, it turns out that there's a second formula for angular momentum. Instead of I times omega, we can shuffle around terms that make up the I and the omega, and we find that it's also equal to mass times the tangential velocity, not the angular. This is the v velocity, the linear velocity, times the radius. So if you multiply these three, you can also get you can also get angular momentum. Either one of the formulas will work, depending on what things you're given in a problem. So you always want to look at the problem and say, what variables are in here? What am I comparing? Am I comparing L and V? Oh, I use this formula. If I'm comparing L and omega, I use the first formula. All right. So again, this formula is analogous to the P equals mv. The mass and the v are the same in both formulas. You're just throwing in a radius to change your tangential velocity into a rotational velocity. So whirling a ball at the end of a long string, a planet going around the sun. These are examples of angular momentum. Once it's going, it's easy to keep going. Of course, you're always applying a centripetal acceleration in the center. In the first case, with the whirling ball, that centripetal acceleration, that pull towards the center, is the tension on the string. That's providing you with your force that pulls it in, the centripetal force. In the case of a planet going around the sun, the force that's pulling in the planet to the sun as it's going around in a circle is just the force of gravity. That's the force that's creating the centripetal force. They're never forces all by themselves. They're created by other things. Tensions, friction, gravity, whatever will pull an object towards the center of where it's spinning, that becomes centripetal acceleration and centripetal force. So angular momentum, it's the external, an external net torque is required to change angular momentum of an object. All right, what does that mean? Well, this is just the rotational version of Newton's first law. In other words, replace the word torque with force, replace the word angular momentum with just regular momentum. An external force is needed to change the momentum of an object. We already learned about that. Torque is necessary to change the rotational momentum of an object. That's all it's saying, right? An object or system of objects will keep its angular momentum as long as no external torque happens on it, external forces that change its rotation. There's an internal force, that centripetal acceleration that's pulling it towards the center, but as long as there are no other forces acting on it, it'll keep spinning around and around forever. So suppose you swirling a can around and suddenly decide to pull the rope in halfway. All right, what have you done? You've changed the radius. You've cut the radius in half. By what factor would the speed of the can increase? Well, you're halving the rope. They're halving the radius. What happens to the V? Well, wait a second. You're going to double. They're inversely proportional. You might say, well, we don't have a formula where one's on one side and one's on the other. Well, we do have the formula of momentum, angular momentum equals mvr. And we're interested in two of these terms that happen to be on the same side of the equation. So if we just rearrange it, we got velocity, the thing we're interested in, that will equal the angular momentum divided by mass divided by radius. And now you can see the velocity, the speed, is inversely proportional to the radius. Whatever happens to one is the opposite of what happens to the other. So if you divide the radius by 2, you will multiply the speed by 2. Right. Conservation of angular momentum. Like regular momentum, there's a conservation of angular momentum. With linear momentum, you learn that before and after a collision or an explosion, if we counted up all the momentum before, it will be exactly equal to counting up all the momentum after all the pieces and all the objects. The same thing happens with angular momentum. If you have some event that happens in the middle, the angular momentum before will be equal to the angular momentum in the end, as long as you don't add some external torque to change things, to muck things up. So it's the same law as the linear, it's just the rotational version of it. So an example of this, and you can do this at home if you have a chair with wheels on it that you can spin on. You could actually take your arms, you don't even need weights, but weights help. You can have these weights sticking out, and you have somebody spin you in a chair. And because angular momentum is equal to I times omega, the rotational inertia times your rotational speed, I times omega, that's the same before and after you do something different. So you get somebody spinning you, and if you were able to, I'm going to start on the right side. So there's somebody spinning you, and they can get you pretty fast, and you're holding the weights on tight. Well, there you have your high speed that you're spinning real fast, but your inertia, your rotational inertia is small because you're keeping all your weight close to you, which is the axis of rotation. You're rotating around the center of your body. But as soon as you stick the weight out, you have moved the mass out, and that increases your rotational inertia. The further you are from the center, the harder it is for you to turn. So your velocity, your rotational speed, will go down. Well, if omega goes down, that's the left side of this. Remember, omega times I has to be a constant in this case, before and after. So if you're increasing your inertia, what's going to happen is you're going to slow down. Your rotational speed will slow down. And you can do this. You can stick your weights out like this. You'll slow down. Pull them back in. You'll start speeding up real fast. Pull them back out. You'll slow down. And this is exactly how skaters, Olympic skaters, do these incredible spins. If you watch them, they're starting with their arms out, and then they pull them in really tight, and they start spinning incredibly fast. Well, they're using conservation of momentum to do this. And you can remember that by this little factoid. So suppose by pulling in the weights, the rotational inertia of a man decreases to half. So we're dropping I to half of I. What factor will the angular velocity change? Well, these two are inversely proportional. You multiply the two together, they equal when you multiply them together afterwards. So if one goes up, the other will go down. So if we cut the rotational inertia in half, we will double the rotational velocity, the rotational speed. And that is because L is a constant in this unless we add some external torque to it. If you want to rearrange the formula, you can see omega equals the constant L divided by your inertia. So omega and I, the omega and the inertia, the rotational velocity and the rotational inertia are inversely proportional to one another. One goes up, one goes down by the same factor, and vice versa. So if you halve the rotational inertia, you'll double your rotational speed. And with that, we'll end here. Thank you very much.